right at the top here, we talk about skewed versus normal versus skewed distributions. And these are just rough examples of what a histogram would look like if it were symmetrical and bell-shaped versus skewed to the left and skewed to the right. All right, so you can see how the tail of the graph is feathering off to the left when you're dealing with a skew to the left, but it's going off to the right when you're dealing with a skew to the right. So it's the direction of the tail, but what I wanted to do here is show you the equivalent box plots, all right? Because you want to be able to come up with this or these relationships without having to create a histogram every time, because we spent a lot of time creating these graphs, but then I just got through telling you moments ago that I recommend the box plot, and then I'm showing you these skew and normal distributions and saying, well, here's some histograms. Well, let's take a look at the box plot variation of it. All right, so I'm just going to draw some generic box plot. So right smack in the middle. So a symmetric box plot is probably the easiest one to kind of identify, because symmetry is symmetry. You know, whether you're in art class or math class, symmetry it's got the same definition. You know, if you were to fold it in half, would the left side match the right side? You know, so that's what's happening here. Left side matches the right side, split evenly over the median. All right, so this is a symmetrical case. So these are my box plots. And so this is the case of the symmetric. Now, when I say a distribution is skewed to the left, I'm also saying it tails to the left. You can make a note of that, tails. So that means that if you kind of imagine that a graph could have a tail, like a dog's tail, like where would that tail be wagging? You know, it would be wagging to the left. That's the taily looking part of it. So what would that look like in the form of a box plot? Those little extreme values, those lines that come off of the box, those are tails. We just want the one on the left to be longer than the one on the right. It really doesn't matter what the box itself looks like, as long as the tail on the left is longer than the tail on the right. All right, so it's skewed left, and again, that's because it tails to the left. And then the skewed right is just a reverse of that. All right, the tail is on the right-hand side rather than the left-hand side. All right, so small tail on the left, long tail on the right. Oop, that took off on me. Back in the game. You know, the length of the tail varies. Sometimes you can call it, you can actually use your own verbiage when you start talking about this stuff. You could say it's slightly skewed right, or massively skewed right, or somewhat skewed right. You can kind of qualify the term. You don't have, it's not just cut and dried. It's skewed this way or skewed that way or symmetric. It's one or the other. It's like sometimes there's gray area, and this is the math class, if there ever was one. This is the math class of gray area. Right there, it's not just black and white. We got everything in the middle too. We live in the gray. To the left. All right, so that's what those distributions look like. And really, I mean, we came up with those methods for coming up with the particular graphs. And so when you have those in mind, it's just like, oh, I created the graph. What does it look like? Which one of these categories does it fall into? And you can easily draw a conclusion. Now, as far as the other plots are concerned, when you're talking about the stem plot or the dot plot, those follow the same relationships as the histograms. All right. So what you see for the histograms, how it tails off one way or the other. Remember, the stem plot is just a shorthand way of making a histogram. So that would follow the same guidelines. Just remember, for this stem plot, you're turning your head or your paper or your computer on its side so that you can look at it from the appropriate perspective. But it would still have the idea, same idea of chunk of the data is going to be grouped together, and then it's going to feather out. It's just a question of in what way does it feather out? Does it feather out to the two tails or just a one tail? You know, how does that go? Right. The next little section, yeah?
Is this a typo? Tails to the left, because this is to the right. Yours is to the left that you drew. Oh. But this is to the
This
right.
is to the right. Yeah. So, talking and chewing gum at the same time.
Can you just give me my points, please?
It's not printed, so yeah.
Okay.
Yeah, those aren't typos. Those are just like, thank you for pointing that out. I'm appreciative. But yeah, you don't get bonus for it. But what you do get is a positive mindset from me when I go into grading your papers and stuff. So it also, I'm like thinking to myself, oh yeah, that was very helpful that one time. We got a good egg here. All right, so maybe I won't take off that half a point.
Kudos
to put the key on the stem plot. You know, things like that. You could toss the part on the bottom. Any references to the TI graphing calculator, you can get rid of all that. I'll take that as a typo. Honestly, I hope to never use this thing again, the TI calculator. But I think I'm stuck with it for some classes. But in this class, I make the rules. Been teaching this class for 20 years. They can't tell me anything about this class that I don't already know. So, you know, that TI calculator had its day. I'm done with it. I'm not making people spend hundreds of dollars anymore on textbooks and calculators. So that's that. Assessing normality is an important concept. We've learned we've learned one way to do it that involves computation. You know, that's the empirical rule, that 68, 95, 99.7% rule. But we also have another technique, and this is it's a normal probability plot. It's another type of graph, but this graph allows you just through some simple computations to be able to come up with an idea of whether or not a graph is normally distributed. All right, so it's kind of you know, it's number crunch heavy, but I'll show you how you can streamline the process in a few minutes. But we'll go through it by hand first, just because it's you know, just to get a sense of the idea. But I do want to start incorporating more and more. Oh, you won't have to do that. Let me get rid of that. People have to look at that. We're going to incorporate more and more, or Excel, Google Sheets and stuff like that, more and more into the class, just because the spreadsheet aspects of those functions, you know, the computational part of those spreadsheets are very, very important and very, very useful. Right. So that's we're going to spend some time on that, just because it's very, very, very much so worth your time. Right. So you know, there's a couple ways we can go. If we want to determine normality, we could use the empirical rule, but we could also use this normal probability plot, right? So the question here says to determine if the following data are normally distributed, all right? So the process here, you must first determine the percentile rank for each score. We do this by finding the average between the rank of the data point and the data point immediately preceding it. Right? So that's going to need further explanation. I'm aware of that. I'll get to that in a minute. Then we divide this result by the total number of values in the data set. Then we find the z-score associated with this percentile using inverse norm function, but that's not something that we're going to do. We're going to do it a different way. All right. So this last line, I'll call that a typo. The TI-84 will graph the probability plot for you. It's not the TI-84, it's Desmos, but let's just get rid of the whole line. So I'll take that as a typo. We're gonna make these notes good by getting rid of all the typos. And again, then we find the z-score associated with this percentile, and then that's that. All right. So we'll start the process of building the table, and then we'll go from there. All right. So at least the percentile part of it. So the key ingredient here is the rank. Now, the percentile rank comes from the position of the value, right? So, and we average that position with the position of the value immediately preceding it. So that first entry, you see where it says percentile right below it, it has this computation, right? That computation comes from the fact that we're living in the first position, and we're saying we want the position of the data point immediately preceding it, the one before it. Well, if there could be a data point prior to the first one, it would be the 0th one. All right, so we start off with a value of 0. We're finding the average of 0 and 1. All right, so 0 and 1 divided by 9. So 0 plus 1, you can take that 1, divided by 2. That, clear. Well, we know that's going to be 1/2, but let me just do it all in one shot. So 0 plus 1 divided by 2. And just to show you, that's your 0.5. But if I go back in, I also want to divide that by 9. That's where that first entry is going to come from, right? So then we can kind of live with this using little Desmos shortcuts that are going to make our lives easier. So let me show you what I mean by that. So the next computation, we're looking at position 2. So it was 0 and 1, position 0, position 1. Now it's position 1 and 2. So 1 plus 2 over 2 divided by 9. So the big question is, all right, well, what about that 9? Where's that 9 coming from? And maybe that's not the big question, but it's a question that I'm sure is on somebody's mind. This is the total number of values. All right, if you count up the number of values, you see that there's a total of 9 of them. All right, so a couple of ways you can handle this on Desmos. One way would be just to go back and edit on the fly. Change the 1 and the 2, or change it into 1 and 2, and then you can get the decimal value and you're good to go. All right, so that part's not bad. I mean, it's a little painstaking, but there is an easier way. I'm going to go 3 decimals here, so 1, 6, 7, or 3 significant digits is what I meant to say. All right, we will have to come up with a z-score based off these percentiles, but that's a different conversation for a few minutes down the road. All right, so
I have a question.
Sure.
Why do you use this equation, like, to find the percentile? Like, I'm just confused as, like, why this is the equation. Like,
oh, because when you're finding a percentile rank of a value, that you're always taking the position of numerical values and dividing it by the total number in the set of data. That's just the process.
Okay. And
yeah. So the idea is that if I were to say that there are, let's say, 30 people in the class, and I got a test score of, let's say, an 80, and I wanted to know what my percentile rank was, I'd be looking for the number of people I performed better than and divide that by the total number of people in the set. And then that would get me the percentile rank. But the way of handling that is to take where my number falls in that list and the one prior to it and average them together. Right?
Oh, okay, got it. So that's why it'll always be divided by 2 because you're trying to find the average of like those two.
Those two positions within the set.
Got it. All right, thank you.
No problem. So next up, I would take the 2 and the 3. So 2 plus 3 divided by 2. I'm going to pause for a second. Sorry, I got to step away for 1 minute. There it is. I didn't have to see the chat to know. Oh, no. Oh, yeah, the question was, are we getting to the z-score? We're getting there. It's coming. All right, so what we can do here is I'm going to just wipe this out so I have a fresh slate to work with. Originally, we were doing, 0 plus 1 over 2 divided by 9, then 1 plus 2 over 2 divided by 9, and so on. The over 2 divided by 2 never changed, so we can keep that consistent. But what we can do is use the letter A and the letter B to represent the first numbers and the second number in the computation. Divided by 2 and divided by 9. All right. So all I did was I just typed in the letters A and B. It's not a special command. I just typed it right in. Now you'll see here that it gives you the option to add a slider. All right. So adding a slider, you can do that for A, you can do it for B separately, or you can do it for both. All right. Any letter that you put in, Desmos will give the option to add a slider. And so I'll do all. And what it'll do is it'll create a slider that allows me to really just kind of navigate my way through the different A and B values. So I'm still going to do the setup because the next part, I'm looking at 4 and 5, 4 plus 5 over 2 divided by 9. Then we're looking at 5 and 6, 6 and 7, 7 and 8, 8 and 9. So you could write all that stuff out. That's all well and good. But this slider approach is going to give you the values in a little bit of a more streamlined way. All right. So if I know, I'm going to bring back purple here. If I know that the A value is going to be 3, then I could slide my slider over to 3. Now, if you don't like sliding, because sometimes, it can kind of hop off. Like you try to slide it to a particular value, like this one, I'm going to try to put to 4 on the first time. It doesn't always land. Sometimes it hops off. It's kind of annoying. So what you can do is just tap on the value and just change it right in the formula. All right. And it'll move it over and it'll give you the value. All right. So 0.389. So the next one was 4 and 5. So make this a 4. See, it's not cooperating. It's kind of annoying. If you're doing it on a computer, it's a little easier. But when you're using a tablet, it can be a little aggravating. So, like if you find that it's just kind of sticking on you, then just tap into it, change the number, and then click into the next field. The next one's got to be a 5. And it'll do it for you, then just kind of click out to make sure it's locked in. So we're looking at 0.5.
Instead of 2 sliders, could you just set B to equal A plus 1?
You could. Yeah, you can play around with it that way. If you know the relationship is always a 1 unit difference, you can go that route. Absolutely.
Cool, thanks.
No problem. So then, the next one, the next pairing, if you want to kind of streamline it, next one we know is going to be 5 and 6. So I kind of got lucky and I hit it without too much effort. So I know that the next one is going to be about 0.611. 6 and 7. See, not quite so lucky on this one. I'm trying, not happening. So I give it a couple of seconds of effort and then I switch over and I just do it manually. Type in the 7, We see we're at 0.722. So then 7 and 8. I tried it, no success. And for me, it's almost exclusively because I have fat fingers. So if you got like little dainty fingers that you know the magic can work, you know, then go for it, you know. But I got these sausage fingers that just not. I mean, they're not as. I've seen some grotesque sausage fingers out there. I mean, they're not that bad, but they're bigger than what my screen is allowing for. So about 0.833. And then at long last, and I'm just going to jump it right in here, 0.8 and 9. At long last, 0.944. All right, so we got percentile ranks. Now, if we convert these over into decimal form, I'm sorry, they're in decimal form, into percent form, then we would actually have an idea of what the percentile values are. Like that number 38.1 occupies roughly the 83rd percentile, which means that value is better than roughly 83% of the data in the set. It's a small data set, so it's not really going to tell us too much, but it's a fair amount of information, and it's good information. So we're in pretty good position there. Now, the big question that comes out of this is like, and it was posed before, it's like, what about the z-score column? All right, yeah, it's a hell of a question because we need that, because when we're plotting, we're going to plot the original data point against its z-score. All right, so what I mean by that is whatever these numbers are here are going to get plotted against these numbers here. I probably could have just increased the size of the highlight, but whatever. It is what it is. So these are going to be your, I'll call them the X values, and these are going to be the Y values. So now they're not really the Y, so I'll put them in like little air quotes here. Not really air quotes, they're really quotes, but I like saying air quotes. All right. So like if you're thinking about an algebra trig class kind of thing, these are the ordinary X and Y values that you would have. So when you're plotting points. All right, so now we just got to come up with those values. All right, easier said than done. Well, it depends. It used to be really kind of a pain, but it's a whole lot easier now, because back in the day, and actually, I got to imagine there's still some teachers out there that make people do it this way, and that is the table method, which is they would make you have, and if you've ever seen a statistics textbook, like a physical one, they usually have the Z tables in the textbook, and those Z tables give you the area under the curve associated with particular Z scores, or under the standard normal curve. And so we would have to, and I remember learning that this way, we would have to refer to those tables in order to come up with Z scores associated with particular areas or percentages, right? No longer is that the case. Now we have calculators that do that for us. So we can take a look in the function menu. You can see that we have all this trig stuff, which we're not going to do anything with. Right? We have stats, which we're going to do a lot with. Okay, and in this stat menu, you see total, length, mean, all these other things. Honestly, there's one that says mad. I have not investigated what that means yet. I don't know what that means. I'm sure that the M stands for, so I can't imagine it actually means that the calculator is mad. But if we go into distributions, you see that we have some other options here where we have PDF, CDF, and inverse CDF, right? We also have histogram, dot plot, and box plot. So that's another conversation for another day, because like I said, we're going to talk about how to make these graphs using technology. And this looks like we're ready to rock and roll. I want to make some graphs. Histogram, dot plot, box plot looks like the place I want to go to. So let's hit on inverse CDF. All right. So if you tap on it, it tells you what you need to have in there. So, for example, try typing 1, 2, 3, and then 1. Right. So the inverse CDF is supposed to report a z-score for a given area. So 0.167. Sorry, I'm thinking of a different function. It actually should have reported the value. Time out. I think I'm thinking of the GeoGebra one again. They're so similar that it's easy to get confused. So let's see. Inverse. Yeah, it's just a calculator. Calculator statistics. What is the MAD mean? I'm just curious about that. MAD? Oh, mean absolute deviation is what MAD stands for. Distributions, okay. Binomial, not what I want. Distribution. Random list. Looking, not seeing it, not seeing it. What on earth? Yes, so the normal distribution, that's fine. What's the other way? They get so lazy in their little descriptions here, and it's so kind of annoying. So we got that binomial, or the normal distribution between 0 and 1. That's okay. We'll create a distribution of functions, okay. Distribution CDF value. And we'll put up the probability run there. That's not what I want. Lower and upper. Oh, lower and upper. I'll put the probability. That's not what we want either. What on earth? Density of value. Ay, ay, ay. This is aggravating. Define the z-score. Oh, really? Oh, that's so annoying. Okay, well, I'll show you. It's not going to be pretty, but this sucks. I think I was thinking of Desmos, but all right. Well, I'll show you the steps, and then we can all lament over just how much of a pain in the ass it is. But it is what it is. So we're typing in the inverse. So it's inverse CDF, and I'll walk through that step in a second. But then, and actually, I'll walk through it now. So function. I just want to get a clean display here. function, inverse CDF. This is the part that you're not going to like. And I'm going to see if I can figure out a workaround because I don't like it either. Then you're going to select normal distribution, which I guess I'm fine with. But then for whatever reason, you close parentheses. That part I don't like at all. And then you type in your decimal. So I'm just going to check it for the first one to make sure it gives the right value. So it works. I just don't like that one bit. All right. So let me just I'll list the steps for this, just because that way it was more convoluted than I've ever seen before. So, and I don't know if they changed it recently or something. I remember that being a whole lot easier. So I'm thinking of GeoGebra or I'm just misremembering completely. Age is a thing. So inverse. So we're selecting the inverse CDF function. Then we open parentheses. Then we select the normal distribution function. Open and close parentheses. All right, and then after that it's comma, the percentile value. All right, so it is what it is, but at least it gets us the value. It's just there's got to be a better way, and I'll effort that. But I'll just show you again. Functions. So you're in the distribution menu, and for the record, I mean, you'd still have to follow some steps and know some procedures on the TI calculator, even if we went down that road. So it's all the same. Inverse, normal, close it up, decimal value of the percentile. All right, so we get the negative about 0.967. All right, rounding appropriately. And then, you know, like, I mean, you could, I suppose, go the slider route here, but I think that can be a little annoying. I mean, if you were to do the slider, just do it real quick. Either way, you're gonna have to type in the decimals. We already used a slider above. We used the letters A and B. So I would need a new letter for this slider. Otherwise, it would refer back to the previous one. So then, you know, C is not defined as anything other than 1, so it's not meaningful. So if I put this slider in, I would change it to 0.278. And it would give me the decimal value of negative 0.589. And then I would just keep manipulating it in here. So 389 would become negative 0.282. 611 becomes 0.282, but positive. 722 becomes 0.589, but positive. So you see the symmetry here. It's the same values, just positive. All right, so there's a little bit of a silver lining here. 0.967. And then the last one, 0.944. We're looking at the 1.59. All right, so That's a bummer. I don't like how convoluted that formula is. But what I can do is I can I'll put together a little, I'll call it a cheat sheet, a Desmos cheat sheet with all the different functions and what they all mean and what they're used for. Just because I'm just so bummed by the fact that that was how that was presented, that it's not reasonable. Right? So now what do we do with this? We plot. All right. So
Quick question.
sure.
What is like, I know you gave us the example of like those as like a rank in a class or whatever, like the 1 through 9. What would the z-score be in that situation, like in a real world problem?
Z-score is talking about how many standard deviations a value is away from the mean. So when you say somebody has a score that's above average or below average, whether it's a body temperature or intelligence quotient, or you start getting into inanimate objects, you know, you can get into like heights and weights, and you can get into gas mileage in cars and stuff like that. When you start getting into z-scores, you're talking about just how far above average and how far below average a value is.
Okay, so like in this case, the 33 would be average.
The 33 would be precisely average, exactly.
Okay, thank you.
So we're plotting now, and you know it's tedious, but it's going to be a meaningful outcome, because the 24.9, again, we're ballparking here. We're going 1, 2, 3, 4, 5. This each tick mark is worth 1 unit. So each one of these is worth 1. So if I'm ballparking 24.9, that's just going to be a shade to the left of 29. All right, so that part is fine. I need to plot it about negative 1.59. So that's going to put it right about, if I had to guesstimate, ballpark it, it's going to put it right about here. All right. The next entry, 28.5, against a little bit shy of negative 1. So that's going to put it like right about. Then 29.4, so a little bit shy of 29.5, so a little bit short of the halfway point between the 29 and 30. That's going to be a little bit more than half a box down, right? So you see I'm talking in terms of a little bit, just about, kind of, sort of. If this point would lock in, that would be great. That's really what we're talking about when we're plotting points. It's just like ballpark values. Right. The next one, 32.1, and then it's only down a smidge. So, you know, the proper statistical terminology, smidge. And 33 is right on the axis. This is killing me. My Apple Pencil died, and I got to slum it and use this crappy one. 33.4. So I'm at 33 with that last point I plotted. 33.4 is just a little bit shy of half of a box to the right, and I just want to go up a smidge from there. So that's where we're at. 36, a little bit more than 36, and a little bit more than half a box. Gonna put me about right here if it would lock in. 38 and change, and a little bit less than 1. That's gonna put me right about, come on, love of everything. I just gotta kind of stab it. I just want to make the points a little bit more noticeable. 40 and change, and a little bit more than 1.5. So it's gonna put me right about like. Now just be careful about the scaling, because I know definitely I kind of lost track of it along the way, but I think I sort of picked it back up at the end. All right. So the big question that I'd be asking if I were in your position, and it's a question that comes up fairly frequently, And it should. It should in this class, definitely more than any other classes. Okay, well, why did we do that? What was the point? Right? Again, the whole idea behind this is to determine, is to determine normality, right? Whether or not a distribution would be considered normal, right? So the general rule of thumb is, and I'll just kind of jot it off on the side, is if that the points follow a linear pattern, right? So if they follow a linear pattern, then your original data set is approximately normally distributed, right? So if, I gotta somehow figure out how I can write this without having a nice working Apple pencil, but I'm gonna force the issue. So if the pattern is linear, then distribution is approximately normal. We never say a distribution is exactly normal. That's not something that exists. There's no exactitude when it comes to normal distributions. Not in the real world anyway. So we just hope for something that looks like it would be kind of, sort of. So we're still coming back to that kind of, sort of. So what I would say here as my conclusion is pattern is somewhat linear, so the distribution is somewhat normal. So the distribution is somewhat normal. The vague terminology, the vague descriptions are actually encouraged in this class because we don't want to speak in absolutes. Only Sith deal in absolutes. You know, we're, like I said before, we're living in the gray. You know, so it's not always an exact answer. It's mostly going to be something like, what is it more like? Is it more linear than nonlinear? Yeah, I think so. You know, so if I were to look at this and say, okay, yeah, I know I can't put a line precisely through all the points, and that's what I mean when I say linear. Can I get a line through a lot of the points? Does it look like it's following a linear path? Yeah, sort of. You know, it doesn't capture every single point, but it doesn't have to, right? Because again, we're not looking for exactly linear cases. I'm looking for something that's approximately linear, right? So something that's in the neighborhood of linear. So therefore, it would be in the neighborhood of being a normally distributed situation. Because a lot of the techniques that we're going to learn about rely on a normal distribution. But if I'm saying that it's just impossible, not impossible, but like so improbable that a distribution will be exactly normal, like all of statistics goes flying out the window. So we have to make some concessions. We got to say, all right, it's not exact, but it's close enough, right? So we make those concessions and allows us to carry on. And then we acknowledge those concessions. What we do is we say, hey, FYI, in this study, I treated it as a normal distribution, even though it wasn't 100% normal. So that the reader has the understanding that, okay, concessions were made. I got to take what I see with a grain of salt, but I do see that the findings have merit, and they lead to maybe some further investigation depending on what the topic is.
Professor, question. Is this a graphical distribution?
Say it again?
Is this a graphical distribution?
This is a type of a graphical distribution, yeah.
Okay.
All right, so when it comes down to determining a normal distribution, you have the two techniques, the empirical rule and the normal probability plot. You could do it either way. Now, I don't think, based on what we've talked about tonight, I don't think I've done such a hot job of selling you on this technique, because this looks so complicated. But what we're going to do next time is we're going to start off talking about Excel and Google Sheets. And I'm going to show you how you can do all of the graphical stuff, histograms, this type of plot, some other kinds of plots, like things that we're going to cover moving forward, that are just going to make things a whole lot easier. So more on that later. You just got to kind of believe me for now that there's a much easier way to do this, that this was just how to, just getting a little insight on the structure of the process, but there is a way that makes this a beneficial approach, or a technique, a technological technique, and that we're going to talk about that next class. All right. So next class, we're going to talk about correlation, regression, and how to do pretty much everything else on using technology. So next class is going to be a very big technology class. All right. So make sure you have access to some comfortable way of accessing Google Sheets. We'll use Google Sheets because I know not everybody has easy access to Microsoft Excel, and Google Sheets will do what we need it to do. All right, so if it means like doing the Zoom through your phone so that you can free up a laptop or another kind of computer or something like that, just try to be prepared in that regard, so that, I know it's really tough to kind of fumble around on a mobile device trying to use spreadsheet software. So if you can have like a laptop or a computer, that would be definitely the way to go. All right, so that's just a little bit of a taste of what's to come. All right, so I'm going to stop the recording here.